Physical science time, we're going to talk about thermodynamics. Thermodynamics. Oh, we love to do, oh no, I don't have a clue if that's true or not. I love to do this. When we have a new word like this, let's break it down. So this is related to, usually when we do this with words, it's one of two other languages that we usually do.
Greek and
Thermo.
Greek or Latin, generally. These happen both to be Greek root words. Thermo meaning
Hot. Well, heat.
heat. Yeah, heat or something that is hot. So you can write that, just jot that down. And then dynamics referring to something that is doing what? Can you guess?
changing.
It's a little bit different than moving. Yeah, moving is what I was going to say. Changing, somewhere between moving and changing, right? So remember, the Greek word for movement itself was kinematis, which is to move, right? So like it's related to the word for cinema and kinetic energy and stuff. Dynamic, I think changing is probably nearer to the truth, but it's something that is in flux, we might say. In fact, the Latin word for it is flux, like in the word fluctuate, right? If your temperature is fluctuating, it's changing over time, right? Anyway, in Greek we call that dynamos, which is to change. So thermodynamics, how can you put it together now? How what changes? How heat changes, right? So how heat changes as it moves around in the environment, or as it removes itself from the environment, or a specific environment. So one thing we're going to talk about before we begin any of this is we need to get in our head this idea of systems. Was it you guys I talked with about systems? We talked about like the solar system and, okay, I think it was, yeah. So when we're talking about systems in the thermodynamic context, we're talking about a specific group of things that are acting together. A specific group of things acting together. What's the biggest system? If we're talking about the biggest system, no, bigger than that.
Galaxy.
Bigger than that.
Universe.
The universe. If we talk about the universe as a whole, all of these things that we talk about today will be true for the universe as a whole, but they're also true for specific and smaller, what we call systems. And there can be closed systems. Can you guess what the other one might be?
Open.
Yeah, you got it. Open systems. So closed systems are where we consider that heat and work do not flow into or out of the system. Heat, what's the abbreviation for heat? Remind me? Q. And work, which is abbreviated W, do not flow into or out of the, well, I was going to say the system, but that stuff. It. Right, that system. I didn't want to use the word system again because that's the word we're defining. Yeah, what's up?
So this is kind of off topic, but is there anything bigger than the universe?
We don't know. Good question. We don't have time to get into it, but no one knows. There's no way to gather evidence about it, so we can't make a scientific claim one way or another. Good question, though. Heat and work do not flow into or out of it, right? So we consider that all that heat, we can think of it even as that heat and work, that amount of energy, can't change because it's all trapped in that one little system, right? Whereas in open systems, let's make this very simple. So if heat and work do not flow into or out of it in a closed system, in an open system, what? Yeah, they do. Out of it? Oh, acting together. Open systems, flow does occur. I was going to put it do. You know what I mean, though. Flow does occur. So there is some influx or outflux. Oh, I even used the little word we just talked about. Right, there's either some changing into the system or changing out. So influx and outflux of heat or work. Anyway, so now that we know about systems, we're gonna move on a little bit, okay? So your book talks about heating systems, internal combustion engines, and refrigeration systems, which we're going to get to eventually, and if we don't have time, you can just look up those things on your own. But the main thing we want to get to today are these 4 laws of thermodynamics. And we're going to, just for the sake of both expediency and because of your average grade level and what we're required to know for the test, we're going to keep these things pretty simple. let me just tell you that there are, like, if you go to a college and you major in science, there are not just classes, but entire, like, course progressions where you would take one class of these each semester of your entire college career about thermodynamics, right? It gets very, very in-depth. But we're just going to get a very surface-level understanding of what the 4 laws of thermodynamics are. So I'm going to try my best to make them not false, but they're going to be pretty, like I said, they're almost facile. Like, we're going to talk about them in a way that is not complicated. Not complicated. We're going to try to leave things as uncomplicated as we can. So which one we got 4 laws of thermodynamics. Which one should we do first?
The first one.
Good enough. You fell into my trap. The zeroth one. We're going to talk about the zeroth one first. So, as we remember from that video, the zeroth law of thermodynamics is named that because, for one thing, there had been historically 3 laws of thermodynamics, and let me make sure. There had been 3 laws of thermodynamics, and a 4th was discovered, but it was considered to be more fundamental than the other 3, and so they named it instead the zeroth law of thermodynamics. So the zeroth law of thermodynamics is that 2 objects of different I want to say temperatures, let's say heats. 2 objects of different heats in a system will, will reach an equilibrium heat. Meaning that if we considered a system of just 2 objects, and there's nothing else involved, and they have different temperatures or heat energies to start with, over time, the heat will flow from the hotter to the cooler until they are at equilibrium, until they have the same heat or temperature. Okay?
So kind of like when you have a fish and you set a bowl of water out so it becomes room temperature?
Yeah. So when you buy a new fish, the water that comes out of your tap is too cold for that fish, probably. And so when you set the bowl of water out for an hour or 2 so that the water temperature will increase in that case, right? Yes, that's correct, because that temperature of that water is reaching equilibrium with the environment. We're bringing them both. So we talked about this a little bit before, but not only is the fishbowl warming up to room temperature, what else is technically happening, even though it's probably not measurable?
The room is cooling down.
Yeah, the environment is cooling down, right? If we consider a small enough system, like if you did this whole thing in a very well-sealed styrofoam box, you could noticeably, you could measure the temperature drop in the box itself while the temperature of the water increased. It might take a while, but that would definitely be true. This relates to, I don't know, I wouldn't call it a joke. It wasn't even, it's not funny or really smart, but I remember reading about this when I was like in 3rd or 4th grade, and I was like, I had a smaller and worse brain then, and it was blown because someone had said, or I read, why does your cup of coffee, why do you say that it cools down and your cup of your iced tea or whatever warms up? I was like, oh, that's so weird. They're both getting to the same temperature, right? But because the iced tea started out colder and then warmed up, we call that warming up, right? And when the coffee started out warm and cooled down, we call that cooling down. It's just more of like a wordplay thing. Anyway, since room temperature is somewhere between those, they both reach room temperature, right? So if we think about our coffee as cooling down, we don't want to drink anymore, or we think of our iced tea as warming up and we don't want to drink anymore, right? Okay, so that's the zeroth law, is that they will reach equilibrium. The first law of thermodynamics, I'm going to make sure I phrase this correctly so that you can get it right on the test. Whatever the total amount of work plus heat, total amount of work plus heat is constant in a system. So, I mean, this counts as scientific work, right? If we consider the system, in my example here, to be this classroom, right? And I do this. Is it work?
Yes.
Yeah, it's scientific work, right? Because I'm applying a force up and this thing is moving up, then I'm applying a force down and it's moving down. I'm doing work, right? So, is the total amount of work increasing in the system? Yeah, but it's also increasing the heat, right? So while the amount of work my body can do, like you can imagine, if I sat here and did this for 30 years, I would probably die of starvation, right? I mean, well before 30 years. I'd probably die of starvation if I could do this for like 30 days. But I'm doing this, eventually I'm going to run out of energy, right? The amount of work that my body can do total is going to deplete. Meanwhile, the amount of what in the room is going to increase the entire time. Heat. So the total amount of work plus heat, right, the potential energy my body has, plus the heat that's already here, is going to be the same before and after. So at the beginning of my stupid little process here, I had a lot of potential energy, a lot of work I could do with my body, and we'll say the heat energy in the room was at some nominal random level, right? Afterward, my body can do much less work now, but there's more heat in the room, right? So the amount of work decreased, so the amount of heat had to increase. So for a system, for any system that we consider, the amount of work plus heat that system has in it stays the same, right? So as you do work, in general, another way to phrase this is that as we do work, what must increase? Heat must increase as we do work, right? You have questions about that one? Let me read you what the book says, just so that we're all on the same page here. It says, according to the first law of thermodynamics, the increase in thermal energy of a system equals the work done on the system plus the heat transferred to the system. Doing work on a system is a way of adding energy to a system. As a result, the temperature of a system can be increased by adding heat to the system, doing work on the system, or both. So within the system, it can't change. But if you have an open system, right, and you add work into it, that amount has to equal the work that was subtracted from the other. And that brings us to the next law of thermodynamics. That brings us to the next one, which is, can you guess?
Second.
Yeah, this one's not a trap. It is just the second law. So the second law of thermodynamics is let's put thermal energy. Thermal energy flows from a warmer object to a cooler, right? And this almost seems like a reiteration of the zeroth law, but it isn't exactly the same. What this is saying is that both of these could technically be true if somehow a closed system was there and the cooler object was getting cooler, right? It would just have to equal the work done to it, right? If the Q was decreasing, some work would have to be doing to it. So that wouldn't violate this, right? If we had a cool object in a warm little styrofoam box and the cool object kept getting colder and colder and colder, right? That wouldn't violate this as long as the amount of work was being done. And it wouldn't violate this as long as equilibrium was maintained. But what this one is saying, this one is making it very clear to us that the energy only flows from warm to cold, right? So thermal energy on its own only flows from warm to cold. What seems to be a violation of that? Like what?
Freezer.
Yeah, a freezer or an air conditioning unit in your house seems to violate the second law of thermodynamics. But what must be happening instead? What must the trade-off be? Something can get cooler, but what does the trade-off have to be? Something else somewhere else is getting warmer, right? So I'll say an idiot. When an idiot is talking about global warming or climate change, they might say something like, "Why don't we all just open up our freezers and make the environment cool down?" Right? And what the answer to that is that while the freezer is cold in the front, right? If you've ever been behind a fridge, it's hot back there. In fact, it's more it's hotter than the room. Then the freezer is colder than the room. Do you see what I mean? Like it's actually, because it's not a perfectly efficient machine, it can't remove more heat than the amount of energy it has to remove heat, right? And so the second law of thermodynamics is telling us that heat only flows, remember heat is the flow of thermal energy, heat only flows from warm to cool. And then the third law, your book doesn't mention it all, so make sure you write this one down. The third law is that let's put it this way, as heat is removed from, let's put thermal energy instead, I'm sorry. As thermal energy is removed from a system, at some point, no more can be removed. And we call this point where no more thermal energy can be removed at all, no matter what. We have a name for that. Can you guess what it is? Absolute zero. The reason I phrased it this way, this is not, I wouldn't say, okay, it is correct, it is not the best explanation. The reason I phrased it this way is because there's a thing that we talk about later when you're in chemistry called entropy. And I don't want to really get into entropy or something else called enthalpy yet, but this really has to do with those two quantities and how they change. But for now, this is true. It's not wrong anyway. It may not be the whole truth, but it's not wrong.